NENOMATICA, where mathematics meets YouTube excellence. Step 1. Express the difference of powers. We write a to the fifth minus 1 as open parenthesis, a close parenthesis to the fifth, minus open parenthesis, 1 close parenthesis to the fifth. We now apply the rule again, exactly as stated. Step 2. Apply the formula with n equal 5 and b equal 1. Using the rule, a to the fifth minus 1 equals a minus 1 times open parenthesis, a to the fourth plus a cubed times 1 plus a squared times 1 squared plus a times 1 cubed plus 1 to the fourth close parenthesis. Step 3. Simplify the terms inside the parentheses. 1 to any positive power equals 1, and multiplying by 1 does not change a term. So the factorization becomes a to the fifth minus 1 equals a minus 1 times a to the fourth plus a cubed plus a squared plus a plus 1. The factorization of a to the fifth minus cubed plus a squared plus a plus 1. In this lesson, we will factor two expressions using the sum and difference of powers. We will start with a to the fifth plus 32, and then factor x to the sixth minus 64. Along the way, I will highlight the pattern so that it clicks visually. First, the rule for the sum of nth powers when n is odd. It says a to the n plus b to the n equals, open parenthesis, a plus b, close parenthesis, times a to the n minus 1, minus a to the n minus 2 times b, plus a to the n minus 3 times b squared, and so on, alternating signs, ending with plus b to the n minus 1. Example 1. Factor a to the fifth plus 32. Step 1. Rewrite 32 as 2 to the fifth. Step 2. Apply the sum rule with n equals 5 and b equals 2. That gives, open parenthesis, a plus 2, close parenthesis, times a to the fourth minus a cubed times 2 plus a squared times 2 squared, minus a times 2 cubed plus 2 to the fourth. Step 3. Simplify each power of 2. 2 squared is 4, 2 cubed is 8, and 2 to the fourth is 16. So the factorization becomes, open parenthesis, a plus 2, close parenthesis, times a to the fourth, minus 2a cubed, plus 4 squared, minus 8a, plus 16. Now the difference rule works for any positive integer, n. It says, a to the n minus b to the n equals, open parenthesis, a minus b, close parenthesis, times a to the n minus 1, plus a to the n minus 2 times b, plus a to the n minus 3 times b squared, and so on, with all plus signs, ending at plus b to the n minus 1. Example 2. Factor x to the sixth minus 64. Step 1. Rewrite 64 as 2 to the sixth. Step 2. Apply the difference rule with n equals 6 and b equals 2. That gives, open parenthesis, x minus 2, close parenthesis, times x to the fifth, plus x to the fourth times 2, plus x cubed times 2 squared, plus x squared times 2 to the third, plus x times 2 to the fourth, plus 2 to the fifth. Step 3. Simplify the powers of 2. 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, and 2 to the fifth is 32. So we get, open parenthesis, x minus 2, close parenthesis, times x to the fifth plus 2x to the fourth plus 4x cubed plus 8x squared plus 16x plus 32. Great work! These are the completed factorizations. In this lesson, we will factor the difference of nth powers step by step and build the idea using a simple geometric sum. Then we will apply it to special cases and a quick challenge. Here is the key rule we are proving and using. It is called the difference of nth powers factorization. Step 1. State the identity we want to show. X to the n minus a to the n equals x minus a times the sum of terms from x to the n minus 1 down to a to the n minus 1. Step 2. Define the geometric sum s. S equals 1 plus a squared up to a to the n minus 1. Step 3. Compute as minus s. Multiply s by a, then subtract s. Watch how the middle terms cancel, leaving a to the n minus 1. Step 4. Factor out s on the left side. We get a minus 1 times s equals a to the n minus 1. Then solve for s. Step 5. Using s, we can write a to the n minus 1 as a minus 1 times the sum a to the n minus 1 down to 1. Step 6. By a similar telescoping idea, we can factor x to the n minus a to the n as x minus a times the mixed power sum. In this lesson, we will factor the difference and the sum of nth powers. We will follow a clean 4-step algorithm, and then practice with a quick challenge at the end. First, the rule for the difference of nth powers. Step 1. Express the difference of powers using the rule. Read it as x to the n minus a to the n equals x minus a times the sum x to the n minus 1 plus x to the n minus 2a, and so on, up to a to the n minus 1. Next, the rule for the sum of nth powers when n is odd. Step 2. Express the sum of powers for odd n. Read it as x to the n plus a to the n equals x plus a times x to the n minus 1 minus x to the n minus 2 plus x to the n minus 3 squared, alternating signs, and continuing up to a to the n minus 1. Step 3. Substitute a becomes negative a inside the difference formula. We write x to the n minus open parenthesis negative a close parenthesis to the n equals x minus open parenthesis negative a close parenthesis times the sum x to the n minus 1 plus x to the n minus 2 times negative a, and so on, with the last term open parenthesis negative a close parenthesis to the n minus 1. When n is odd, negative a to the n becomes negative a to the n, so the left side becomes x to the n plus a to the n, and the inside some alternate signs accordingly. Step 4. Write the sum of powers formula explicitly. We conclude x to the n plus a to the n equals x plus a times the alternating sum x to the n minus 1 minus x to the n minus 2 a plus x to the n minus 3 squared, continuing up to a to the n minus 1. Great work! Here are the two key formulas. We are going to solve a challenging-looking equation by spotting a powerful pattern. The expression has very high exponents, but a beautiful structure makes it simple. We will also confirm the final answer visually. First, I want to highlight a pattern. Let capital A be x plus 1 and capital B be x minus 2. The long sum you see is exactly what you get when you expand the quotient a to the power n minus b to the power n, all divided by a minus b. It is the classic difference of powers identity. The sum we were given matches the long sum in the identity, with n equal to 1384. So if we multiply both sides by a minus b, which is x plus 1 minus parenthesis x minus 2 parenthesis, the left side collapses to a to the power 1384 minus b to the power 1384. From this equation, we have a to the power 1384 equals b to the power 1384. Because the exponent is even, this implies the absolute value of a equals the absolute value of b. Substitute back a equals x plus 1, b equals x minus 2. Absolute value of x plus 1 equals absolute value of x minus 2. The equation absolute value of x plus 1 equals absolute value of x minus 2 splits into two linear cases. Case 1 x plus 1 equals x minus 2. This would say 1 equals negative 2, which is impossible. Case 2x plus 1 equals negative of x minus 2. This gives x plus 1 equals negative x plus 2, so 2x equals 1, and x equals 1/2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.